And when we started with controllability, just as a brief recap, how can you intuitively define what is controllability? What is controllability? Intuitively speaking.
If I can reach like any state I want with a given input.
Exactly. So, starting from an initial state, can I reach any other possible state in the system? Okay. Given that I wait for long enough and I can provide as much input energy as needed. Okay. To, of course, restrictions, but you will see that we can also live with a little bit less restrictive conditions. Okay, so that's intuitively what controllability means. A checkable condition we obtained going through the argument, basically looking at a solution of our system model, applying Kelly-Hamilton's theorem, and we arrived at what we call the Kalman controllability matrix and the rank condition associated with it. Basically, if the span of our input vector and the successive application of this input vector to the dynamics, so products A times B, A squared times B, up until A n minus 1 times B, if this span is the full space, then we have controllability. So this is, as you maybe can intuitively think of this, this is the iterative application of an input to our system, first directly through the input, this would be B, then with basically one loop going through the dynamics, so that it's A times B and so on. If we continue this for long enough, then we have explored everything that we can reach, and if this is the full space, the system is controllable. If the system is fully controllable, then we can transform it into what we call the controllability canonical form. This is a specific state-space representation where we have, again, a chain of integrators. We have feedback paths which involve the coefficients of the characteristic polynomial, which are neatly assembled in this first row of the dynamics matrix in this specific canonical form. Right, you can see them here. And if you want the numerator polynomial of the associated transfer function, this is a feed-forward path, which as a linear combination forms the output, can be seen on top here. So we have a feedback path here, feedbacks always with scaled with the coefficients of the characteristic polynomial. The output is assembled as the linear interconnection or superposition of the states weighted with the coefficients of the numerator polynomial of the transfer function. That's how this canonical form looks like. Okay. We can bring it into this canonical form. Check, this is, I think, on this slide. I just went over this very briefly last time, and I don't want to put too much emphasis on it, but just to show that indeed, by just comparing the specific form of our A matrix and B vector in this canonical form with the general state space representation, you can basically set up an iterative procedure which allows us to compute the transformation matrix. This TA and this TA involves, maybe that's something that I can point out, this involves PC minus 1. PC, this is the Kalman controllability matrix. And therefore, this transformation into the controllability canonical form is only possible if the system is controllable, because otherwise this inverse will not exist. If we cannot reach the full space, then we have rank deficiency, and then we wouldn't find the inverse of PC. That is what we need in order to obtain this transformation, just as a justification. Okay, and if you want, you can go through this. It's just that we compare iteratively column by column of our desired transformation, and we finally get the conditions for our general transformation matrix. Okay, we have shown this by using an example, the example of the RLC circuit. We started out in the modeling chapter. We have seen that this example indeed defines a controllable system. Okay, so controllability is something that we often obtain, of course not in all cases, but in many cases we indeed face controllable systems. Okay, so how can we now use that in order to control systems? That's the next part I want to address. How can we design state feedback controls? In general, a state feedback control law, as the name says, should involve the state x of t. Okay? But in principle, we are not restricted how we design the controller. So we could think of the controller being a dynamical system itself. So something of the same type as our plan system. This is the plan. This is the plan system. And I've, again, for simplicity, assumed that we have the CISO case without feed-through, but part of this will also hold in the case that we have MIMO, multiple inputs, multiple outputs, and that we have feed-through. So this does not affect the argument, but it's a simple case. These are the dynamical equations of our plan system, and in principle, we could design a controller which is itself a dynamical system again. Okay? To start with, we don't want to use all the possible degrees of freedom that we have, but we want to start with the most basic possibility of a state feedback controller, and that's what is given here. We want to ask the question, is it possible to design suitable controllers, whatever suitable means, but we'll talk about that soon, suitable controllers using a static, a linear static state feedback law. So suitable would mean what would be our main requirements. What should the controller do? What would be the typical requirements for our controller to achieve? What do you think? What would be typical requirements for a controller to achieve? What should the controller do? Yes?
It will be the value of deviation from the value that it should.
Okay. So it should be, in some way, it should give us good performance. Good performance, so we want good performance. This could be, you mentioned, I think, reference tracking, right? Reference tracking. So in the case of the DC motor, if you want to set a constant speed, then you would like to see the controller achieve this constant speed without any control error, right? Stationary control error. So good performance would be something that we certainly require, even more basic or other requirements that you could think of. But the most basic requirement that a controller should achieve is probably the most basic. Always hard to discuss whether we understand the same thing if I use an adjective as most basic, but what would be a very fundamental requirement for a controller in light of what we talked about 2 weeks ago?
To stabilize.
Absolutely. Stabilize the system, right? Stabilize the closed loop system. Okay, so it should definitely stabilize, and in addition, it should possibly achieve some performance tasks. Okay, and whatever these performance tasks are, and however we we specify them. So that would be the requirement. And now, maybe to look at this in more detail. So, the simplest state feedback controller would be one where we say our input would be something. I use the minus sign mainly in order to stress that we have a negative feedback. That is just a linear combination of our state, right? Plus possibly some new reference input V. So that would be the idea. It's just a linear, static. K is not time dependent. There's just one K for everything. And that's just basically a weighted sum of the current state that we feed back as the input to our system. Okay? Can't get simpler than that. The question now is, what can we achieve with such a simple control? Okay. If we set up our closed loop, if you want, then that we set up the system. So what we would have is, in a signal flow type of graph, we would have the input entering via the input vector B. This goes into a summation point. Here I have my x dot, which I integrate to obtain x. I feed back the dynamics matrix A, and then I multiply this with the CT to obtain the output. Now if I want to close the loop, in this case what I would do is I would extract this state. I would plug in my controller state feedback controller gain K, and I would bring this back in order to close the loop with a negative feedback input, and I would use a new reference V to command the system, for example, in order to achieve a reference. So that would be the setting that we are talking about. Very simple, closed loop. So this would be closed loop. Signal flow graph. And so what do we obtain as closed loop dynamics? What do we obtain as closed loop dynamics? Let's say that this is my plant, okay? My plant, that's called the sigma. This is the standard AX plus B times U, Y equals C transpose X. I have the controller. This part. This would be the state feedback controller. As you can see, and that is just a specified above. This is just a static feedback log. Constant scaling matrix K. Now if we combine everything, then we obtain closed loop x dot equals what do we obtain? Closed loop dynamics. If we combine these two equations, we interconnect them using standard negative feedback.
Substitute U.
Exactly. And then what do we obtain? So if we plug in this U in here, what do we obtain? X dot equals We plug it together. What do we get?
AX plus BV minus BK transpose X.
Okay, exactly. And now if I already factor this, then I get an A minus B times K transpose. I can factor out the X here. Plus a B times V. Okay? And the output remains C transpose X. Okay? So that's what I get if I combine sigma and sigma C, the controller and the fan. That's what we get. So, what can we say about the dynamics of the closed loop then? What do they depend on? And what can we say about the dynamics actually? What's an information that we are getting from this interconnection? So what do we have to look at if you want to know how does the closed loop behave?
A minus BK.
A minus BK. T, exactly. This here, this is the new dynamics matrix. This is the dynamics matrix of the closed loop. Okay, so that's what we get. And if you want to analyze it, what can we extract from A minus BKT?
Transfer function.
We could determine a transfer function, okay? If I just look at A minus BKT, then I can still extract something which I can also extract from the transfer function, namely eigenvalues. And that is the poles of the closed loop, right? This I can directly extract. So the dynamics, if you want the poles of the closed loop, are therefore determined by lambda I minus A plus B KT determinant equals 0. Okay, so we determine the eigenvalues of A minus B KT, and this would be the eigenvalues of the closed loop. And now our requirement was that the controller should stabilize the loop, so all these poles should be in the left half plane. And if you want performance, then what would be the best thing that we could get from such a controller? And there's maybe a difference compared to PID control, where we typically don't talk about the poles of the closed loop. Right? In PID control, we talk about the three tuning loops. But here, what you could say is basically the question: where can we shift these closed loop poles, starting from the open loop poles? Where can we shift them? What can we do with these poles? Okay. And the ideal case would be what we then call pole placement. You as a design engineer, you can specify, I want my poles here. Now find a controller which shifts the poles to this location. Because if we remember, what can we do with pole placement? If we assign poles, what can we do? Which capabilities do we have in terms of the dynamics of the system? What can we do by placing poles? What would this affect if you set poles? Assign poles.
Stability.
Sorry?
Stability.
Stability, as we said, is the main requirement, so all the poles should be in the left half plane. But what in addition, now also concerning performance, can we do? What would this affect the location of the poles?
How fast the system changes.
Exactly, so the further left we shift them, so the real part, this has to do with how fast the system dies out, right? The system response. If we just let it move freely, right? How quickly it goes to 0, how fast it moves. Okay? What else? This is the real part. What about the imaginary part?
The frequency.
So the oscillatory behavior of the system, right? If we assign poles in the system, the plant is oscillatory. You could assign poles which are not oscillatory if you do not want oscillations in the system. So you can adjust the response speed, right? You can adjust how oscillatory the system is. You can basically change everything you want. Okay? That's the power of pole placement. And the question is, with such a simple thing, just a simple static feedback, can we do this? Can we assign poles or to what limits? And the answer is basically, so here you can see the structure. The answer is basically given by another canonical form, a controller canonical form, and the answer will be, if the system A is fully controllable, then with this simple static feedback law we can assign any poles we want. So we have full control of the closed loop, and we can do this there. Reason being, you can basically find a transformation. So this is the controller canonical form. This is a transformation again, if the system is fully controllable. And remember again that we have a transfer function then with a characteristic polynomial specified by the coefficients A, and a numerator polynomial specified with the coefficients B. It allows us, basically in a very similar form as the controllability canonical form, to find a specific representation of the system where, again, we have a row of the dynamics matrix which involves the coefficients of the characteristic polynomial. Right? So these here, they are just all assembled now in the last row of this canonical form. Now in ascending order, right? In the case of the controllability canonical form, they were arranged here in descending order. Okay, here they are now in ascending order. The vector B again looks very similar. It has also just one entry where the input acts on the dynamics, and this is in the last row. We again have a chain of integrators, right? You can see that the diagonal now above the main diagonal. This is a diagonal with only ones, which indicates again a chain of integrators. And the coefficients of the numerator polynomial, they again appear in the output vector. And of course it is always understood that if the largest coefficient here is Bm, all the others are 0, right? So if we have only B0, and we only have B0 here and zeros everywhere, and we can fill it up until Bn minus 1. This is the max we can do, right? That's what it means. Now, can you already see why this is the proof that we can achieve full freedom in terms of pole placement if we can bring it to such a representation? Now remember, what we are doing is we are feeding back the state through the input, and basically a linear combination of the states, the current states, but always the same linear combination. Why would this allow us to affect the dynamics in any arbitrary way we want? But what happens if I let the u be a k times x minus k times x? So k times x is just a linear combination, right? It's sum alpha 1, x1, alpha 2, x2, and so on. And they all enter here in this last row, because up the top, nothing changes, right? So in effect, if I bring this in here, each coefficient of my feedback matrix, or vector k, will basically shift one of the coefficients of the characteristic polynomials, because I have an alpha 1 x1, so this will act here. It will shift the a0 by means of an alpha 1 wherever I want to shift it. And the same for all the other coefficients. So I have exactly one coefficient to change this last row. And since that then is the dynamics matrix of the closed loop, these must be the coefficients of the characteristic polynomial of the closed loop. If I shift it on these coefficients to wherever I want them, I can achieve any characteristic polynomial for the closed group. Okay, so that's the idea. That's why it works. Okay. We'll soon have a look at this, but I want to just draw the signal flow graph. Yes.
In terms of the relationship between stability and controllability,
Yeah.
can a system be controllable, like a stable system and an unstable system as well?
Right.
Can they both be controllable?
Yeah. So these are in principle totally distinct properties, right? A system can be stable and controllable, stable and not controllable. It can be unstable and controllable. It can be unstable and uncontrollable. And the worst thing would be
Unstable and uncontrollable.
exactly. So if it's unstable and uncontrollable, and we will look at this in more detail still, if the unstable eigenmodes are uncontrollable, then we are lost, right? Then we cannot stabilize the system. There is no way we can do that, okay? And it doesn't matter what type of feedback we can use out, right? But as long as at least the unstable modes are controllable, we can bring the system at least to a stable state, okay? And it's probably not uncommon that a system could be unstable. I mean, unstable systems are rather rare, but if a system is unstable, then very often it is luckily controllable. Otherwise, it's the wrong design, you would say, right? Yeah. Okay, but it's a good point. They are not related, right? And we'll look at this when we talk about Kalman compositions. I just want to briefly introduce the signal flow graph here. You can see again the chain of integrators. x1 dot equals x2, x2 dot equals x3, and so on, until xn dot, which is then a linear combination of everything. So basically, we have our input u coming in here. We have the xn dot, which we integrate to obtain the xn, and we basically feed back. If we do, I should have done this, right? So this would be the chain of integrators. I have my feedback with an a, in this case I have the an minus 1 with a minus, and now I integrate further, just do this, I integrate further until the x1. Each state is fed back, so this would be the xn minus 1, an minus 2. All of them negatively fed back. This one will be a0. So all of them negatively. So this would be basically these coefficients, negative feedback. And again, the output is assembled from from a linear combination of the states. Each state has a weight, and this is the coefficient of the corresponding coefficient of the numerator polynomial of the transfer function. Okay, and so here it comes. 0, and this is the y, and this here would be the feed-forward path, right? So that's how this canonical form can be interpreted in terms of the signal flow graph, and as you will see, all of them have similar characteristics. All of them have a chain of integrators. They have the negative feedback, and they have the forward path. The transformation which allows me to transform a general state space representation, fully controllable, into this controller canonical form, again can be found in a similar manner as presented for controllability. You basically compare, look at the transformed and the original version of your input vector and your dynamics matrix, and you compare column by column, and that gives you just algebraic conditions for the transformation matrix. And again, this will involve the version of PC, the column controllability matrix, in that it requires controllability. Okay, so that just here. But now the reason why we introduce that is, of course, if we now take this, so we take our arbitrary but fully controllable plant, transform it into controller canonical form, then we can see how, in fact, we can place poles, right? And that's I attach here. It's also, I think, given on the next slide. So if you basically you have your plant in controller canonical form, and you have your state feedback controller, then your A minus BKT is a matrix where we have, so do it once like this. So here I have my chain of integrators. This is all zeros. This is all zeros. And sorry, here I have my this. Here I have my minus A0. Here I have my minus A1 up until the minus AN minus 1. Okay. So this would be the A minus the B, which is 0, 0, 1. And now some K, transpose, so K1, K2 up until Kn, n of these coefficients. And thus, what I get here is one big dynamics matrix where here I have my minus K0, but now I get a minus K1 here, right? Minus K1. I get a minus K1 minus K2, so it's just a shift of the index. I could have called the coefficients K0 to Kn minus 1, that would be the same index, but I guess it's not a problem if we write it down like this. So basically that's what we get. And so this here is now the coefficient of the characteristic polynomial of the closed loop. And we have one coefficient of k, the k vector, to basically move this to any desired location. Okay? So you define p desired of lambda, which would be some alpha 0 plus alpha 1 lambda plus and so on, alpha n minus 1 lambda n minus 1. This is the desired characteristic polynomial of the first loop. Okay? Whatever we design as engineers in terms of pole placement, you specify what the poles should be, or eigenvalues, and then from this it follows that alpha 0 is minus A0, or basically plus A0 plus K1, or K1 is alpha 0 minus A0, right? And in a similar fashion up until alpha n minus 1, which equals an an minus 1 plus Kn, and thus K1 can be computed as alpha 0 minus A0. So this would be the so-called Ackermann formula. It gives you a direct computation of your state feedback controller. And you see it's very, very simple. Okay, just like this. In fact, you can use different algorithms to do that, and the command plane place in my head is such a different algorithm in order to complete these coefficients. You can do it also, well, in the way explicitly. We will do this right away for an example. But that's the general Ackermann formula for a CISO system controllable that shows how I can design my state feedback in order to fully place the pose, assign the pose, whatever I want. Okay? Any questions here? Any remarks? Any comments? And I hope you, yeah.
Where does the alpha come from?
This is the desired polynomial. So this is what you as a control engineer, you basically set this polynomial. You say, I want my poles here, here, and here. And of course, in practice, it might be an iterative procedure, right? But that is a good point. How do we get the correct poles, right? In terms of PID, you know you have 3 knobs to tune. Here you have a full half plane to shift poles. Okay, so in a way, there's much more freedom. You still have n coefficients, so in the case of a second order system, you have just 2 coefficients, right? In PID case, you have 3 knobs, here you have 2 knobs if you want, but these knobs you can basically place, or you can basically do whatever you want with these. Now, there are a couple of things to consider. The idea that we can place the poles arbitrarily is theoretically correct, right? It can be done. However, practical limitations such as input constraints, they still have to be considered in practice. So you can assign these poles at -1 million, but probably this will lead to inputs which exceed your constraints, and thus you cannot really implement it. And thus you will not obtain the dynamics that you have designed there. Okay? And this is what I mean by an iterative procedure. If we do not include constraints in our design, then we probably have to make a couple of loops in order to find the correct pole locations that work for us, which means that at least they make the system stable and we achieve the desired performance given by us in terms of requirements, such as in terms of the DC motor, we want, for example, just 0.1 second of delay when we basically until we reach our 5% tolerance band of our stationary value, or any other requirement, it will be fine. I mean, you can define these requirements, then you design the poles, you probably go through a couple of loops, and then you have achieved the design. Okay? We will see later that we can find controller design schemes which basically take these degrees of freedom and convert them by means of optimization procedures into something which definitely, or which basically reduces then the freedom that we have, the total freedom of placing the poles. But in the general case, this is what we can do. Okay? So it's very powerful. You can do anything you want, right? But I think the considerations are. Okay, question? Yeah?
What states you observed with that?
Sorry?
So what states or what kind of states you observed with that? Because so this controller is placed in the feedback pattern.
Yes.
If I understand it
Yes.
correct. So what are the states? I have a system where I look at multiple states, but I only have one option to power this or to change the behavior of this system. How can I understand this?
So the state is basically the internal mechanism, an internal describes the system fully, let's say that, right? The state is something that evolves in time. Okay? And I always take the current state vector, weigh this. So what K does is just construct, design a linear combination of the individual states and take this as a feedback for you. Okay? That's how control law works. I don't know what your specific question was. So an intuitive idea how this works is, instead of taking, in terms of PID, I take the output, or basically error, reference minus current output. I take this error, I take an integral of the error, and you take a derivative of the other in weighted theory. Okay, that's the idea. Here in this case, I take the internal state, weigh it, and feed it back. Okay? For stabilization. Okay? This is more powerful because, in fact, I take the full internal mechanism. Now, one problem with implementation is I typically don't have the state available. I only have the output. And I'll show you, probably by the end of this lecture or the beginning of the next, that even if we only have the output available to us, we can still implement something which has this property. Okay, so don't worry about the restriction that in fact you do not have the state to feed it back. So this control loop that I've drawn here, this is in fact not implementable because we do not have X. This is not available, only this is available. So we in fact have to extend that, make this a control law which uses Y, but the power of this idea will be carried over and we can use the same thing if we just take the Y. Okay? And then you could now compare this to PID. Where in PID you also take the output Y, but you possibly don't have, or at least it's not clearly, it's not explained directly whether you have the same degrees of freedom as here. Okay? It's a different idea, and it uses the internal mechanism of the system, if you like. Yeah, yes, no. Yeah, of course, we'll have to make an example maybe to see that, and I'll give you also a couple of simulation examples. And next time in the tutorial, you can also design something which then works with a state feedback controller, and you'll hopefully get a bit more of a feeling of how this works. Okay? But it's, in a way, it's magic that if you take the state and you just take a linear combination of the current state, and it's always the same linear combination, it's really the simplest thing that you could do, and with this you can already achieve everything you want. Okay? Right. So here again, a summary of what I just tried to derive on the board. So I start with this would be my plant system this is my plant in controller canonical form. This has open loop poles given by the coefficient of the characteristic polynomial, right? These, whatever the dynamics here are, these coefficients which define the dynamical behavior, they're given here, right? Last one. Now I use my static state feedback law, and I obtain the shifted. So these would be closed loop, dynamics. And this would be the coefficients of closed loop characteristic polynomial. And I can shift them now in the sense this would be my desired characteristic polynomial, whatever I want to specify, and you can basically think of this as something like, if you want, a lambda minus lambda 1 desired. Okay, so this is the way you could specify it. You say, my first pole should be lambda 1 desired. My second pole is lambda 2 desired. And so on, until lambda minus lambda n desired. So now you have specified all of these poles that you want. For each mode, if you want of the system, you can specify one corresponding eigenvalue. And then that's how you can achieve that. So you basically match this here with this here. The 0 with this here. Okay? And you match this here, this and so on. Right? All of these are just matched. And this in the end leads to the so-called Ackermann formula, because if you basically revert this control the canonical representation, then this is the expression that you get for your original state space. Okay? So that's how you can compute the K. Algorithmic procedure implemented in any numerical project program. That's what you can do. You just need A and B and your desired pose. So in MATLAB, you can use place A, B, and the desired pose. I just call this pose as a vector. Okay, or there's also the command Ackermann, where again you specify A and B, so the matrices of your state differential equation between the original coordinates and the desired pose, and that's the way how we can compute the K. Okay? The only difference here is Ackermann allows you to place these poles if you want all at the same location. The place command needs, depending on the structure of A and B, but it needs different distinct poles. Okay, not you cannot specify the same pole twice, for example. Okay, but it's just the algorithmic procedure. But in principle, you can of course also specify the same pole n times, and you need the command Ackermann. Did it get clear? An idea of how you do that, right? And what the power of this principle is. Okay, what we can basically do is we can do the same thing now for our example, second order system. Let's do that. And now maybe not to make this too. Let's do this. I'll just specify, okay, it's simple, but in fact we don't want to, okay, set R10, L, Henry, and C, not really realistic values, but just that you can compute. And now, what would be our desired pose? What do we want? Any ideas? Who wants to specify a pole?
Like a complex conjugate.
If you want. So P12, if you want something complex conjugate, what do you want?
-2 plus minus 1j.
Okay, so -2 plus minus j. Okay, what is the feedback vector k? You can work in pairs. Try it out. Not just in pairs and groups, right? However, how many you want to include? Just try to compute it. Right, you can see A, B, C, and that's all we need. A, B, C, all we need. cooperate if you want. Right? Now is the time to work together. In the exam you cannot work together, but here you have all the freedom, peace that you want.
You're just writing that down very, very neatly and taking it.
I thought that this is space, but since everything's one, it doesn't really make sense.
I mean, it's one, it's so important, but state space is just too much on the chair forever. Don't really get where to put in the.
How to start this? So how to start is to compute the polynomial of a closed loop, okay? Which is just lambda I minus a plus bk, and you have a variable k. Right? K is to be computed, and we just set this as k1, k2. This can be simplified a little bit, and the nice thing is that we always get something which leads to a linear system of equations. It's never a non-linear system, at least in the case of k, so that makes it always computable for us by hand. That's what we get. And this is the characteristic polynomial, the desired one, that we specify due to the choice of our desired poles. Okay? So this is the desired polynomial. So this is the desired polynomial, if you want. Yes. Lambda. Here, that's the polynomial that we get in general. And now we just have to match the coefficients. That's always in terms of polynomials. If you want to make them equal, then we basically set the zero coefficient equal to this whole thing. And you can see that this simplifies quite a lot in this example. And we equate this coefficient to this, and then you get k1 and k2. It's just a simple system of linear equations. Okay, in this case, with the simplified numerical values 1 and minus 1, and the poles that we chose, that's what we obtained. And in fact, you could have chosen whatever you want. You just get different coefficients here, and you can always solve this as a system of linear equations, right? If you can also write that, of course, as if you want. K1, K2. So this equals 4 and 5, and this is right? So we get a 1 and 1 here. 1 and 1 equals then 4. Sorry, 3. Subtract the 1. And in the other case, we get a 1, 0, and this is equal to 4. Okay? That's what we have. Just a system of linear equations. If you take the resulting equations into this. Okay? I double checked this also in MATLAB. First of all, if I set R, L, and C to 1, what we could have done is first to check what are the poles of those two. In fact, they were not very distinct to what we chose in the end, so they were at minus 1/2, plus minus, I think this is probably square root of 3 over 2. So minus 0.86. plus minus j, so they were complex conjugate. Now if I specify I want my desired pose to be minus 2 plus minus j, so quite a bit faster, 4 times faster in terms of the real part of this pose, a little bit more oscillatory even, but okay. Then that's what we get. We can use the place command just as I mentioned, and we get the desired eigenvalues here as a check, okay? And you can also do the same thing with the Ackermann formula, and that is now a comparison of the step response of the system. So in blue is the uncontrolled system. So in blue is the uncontrolled system, in red is the controlled system, and what you can see is that probably we reach the 5 plus minus 5% band roughly, maybe even a little bit earlier, so roughly after 2.something seconds here, and in the other case you probably need some 6, 7 seconds, so it should be 4 times slower. You notice also that we still get an overshoot, right? We could also design these poles, in fact that was the Ackermann formula, let's check, let's do that. With the, I have different poles here, but let's use the ones that you specified. Let's do this again, and check the picture here just. Still, yeah, so this is I think the same picture, that was the same one. But of course I could increase the pose. Check what we can use here. I used Q desired and I used the coefficients. So let's do this. I specify the pose only in one place. And let's now make them, I don't know, minus 100, minus 101. So much, much faster. And non-oscillatory, at least this pose. So now this is what we get here. Okay, observe, this is still the same blue system that we had before. And for the control system, what we would have to do for the step response is to probably zoom in here, but you certainly can see that very quickly we have gone to our to 0 basically, or to our, say, to 1, to our stationary value. So it takes maybe 0.1 seconds rather than 6 seconds or so, but at the expense of a huge overshoot here. Okay? But you could ask, why do we have an overshoot if we have placed the poles on a real line? Right? There shouldn't be an overshoot. Right? The reason for this is, I've checked this here, this system has a 0. Okay? The RSC circuit has a 0 also, so it's in fact a PVC2. And this 0 is unaffected by our whole placement. Okay? So we do not change the numerator part. And the 0 is responsible for this overshoot, so we cannot get rid of this overshoot by basically designing our state feedback. That's the reason, okay? But we can make it arbitrarily fast. The overshoot, however, gets really, really big. And this would probably also mean that in terms of our input, not probably this here, but our input will then also be really, really large if we make this, the pose really, really fast. And of course, in practice, there's probably a limitation, and this might not be cheap. But as you've seen, something like the original choice, which was something closer to what we can do, this yields a better system response, and that probably is also within the constraints. Now, if you are asking, how can I know? How should I design? Well, this is of course something, there is probably no strict guideline, do it like this or do it like that, right? There is of course an alternative to just being left alone with a big half plane, and that is specify your performance in terms of an optimization criteria. And that is what model control would be like. That you specify an optimization criteria and you design your controller based on that. We'll talk about it towards the end of the course. Okay? So, this should have shown first how you can compute the pole placement and thus the state feedback on paper. Hans given you the algorithm, and I've shown a little simulation experiment what this means in terms of performance, nominal performance, everything ideal in terms of simulation. Okay? Any questions regarding that? Anything you want to add? Want to know more? Comments? Okay. No questions at this point? So we could have the break now, 10 minutes break now, and then we continue with observability if you want. Okay? So at 4:30, then we shift the break a little bit. So at 3:30, we continue then and start with observability. Okay? And then we turn this into an output feedback and see that it still works.
I just observability question last paper.